chapter 7. We have in fact already started chapter 7, which is about series of real numbers, particularly infinite series. Now we have seen in the previous analysis video that before we go to infinite series, we need to develop a theory of finite series, and that's what the first section is about, finite series of real numbers. And in fact we have already gone through this definition of a finite series of real numbers. We saw that there are some minor issues with this definition which we will address when we solve the exercises. Now, without going to the actual intricacies of this recursive definition, we have in fact a fairly good idea about what a finite series of real numbers means. We are given a finite sequence of real numbers. For example, this. Say this sequence of real numbers. M and N are actually any integers, so each one of them can be negative also. Now for this sequence, the corresponding series is this sum, a minus 3 plus a minus 2 plus a minus 1 plus a naught plus a 1, which is slightly non-rigorous, but it will work for us. This idea that we have is in fact, it matches with what is given in the recursive definition, and this will work for us. We will go to the actual recursive definition in the exercises and we will address all those issues. How exactly we have used the principle of recursive definition to get this one, and for example, what is an plus 1, because we don't see any an plus 1 here. So we will address those issues, but for now this idea of a finite series of real numbers is enough for our purposes. And the definition also tells us that if we have a series in which this m is greater than n, then it's defined to be equal to 0. So let's go ahead with this idea that we already have about the meaning of a series and see what comes next. Now the definition is immediately followed by a remark, which is nothing very major, but nonetheless it's there in the text, so let's just see it. It's the second item of this section 2. The difference between sum and series is a subtle linguistic one. Let's just first see what the author is saying in this remark, and then we will try to make sense of it. Strictly speaking, a series is an expression of this form. this series is mathematically but not semantically the same thing as its sum equal to a real number. Okay. Which is then the sum of the series. For instance, this expression, the sum of the first 5 positive integers, is a series. That means a finite series is a series and whose sum is 15. If one were to be very picky about semantics, one would not consider 15 a series and one would not consider this series a sum. Despite the two expressions having the same value. So what the author is saying here is that there is a subtle difference between a finite series such as this one and its sum, and the difference is a semantic difference. Semantics, syntax, these are linguistic terms. Syntax is about how you arrange the symbols in a language, and it's about those arrangements, roughly speaking, okay. and semantics is about assigning meaning to those arrangements. So if you just simply, for example, think of this as an arrangement of these symbols and the plus symbol, then semantically these two things are different because they look different. But once we assign this real number as a sum to this series, then in that sense they become mathematically equal, but semantically they are different. If this is somewhat difficult to understand, what is the difference between this and this, then just forget about it. It is not something that is that will be used mathematically. In fact, we would be advised now by the author to forget about this difference. So that's what he is saying. If one were to be very picky about semantics, one would not consider 15 as generally we do not consider 15 as series, and one would not consider this series as sum. This, however, we do all the time, because you see, when I wrote this down, I said that the sum of the first 5 positive integers, we treat this as a sum. However, truly speaking, the sum is the real number that we are assigning to this. Okay. The distinction between these two things may not be so apparent here in the case of a finite series. However, for infinite series it will be very apparent, because here there is already a meaning to this sum. Okay, it's not just an arbitrary combination of mathematical symbols. This expression already has a meaning and it already has an assigned value, and that value is 15. However, if you look at an expression like this, I am prematurely bringing in infinite series, but just for the sake of understanding, if you look at an expression like this, where we do have again mathematical symbols thrown in, so this is an expression, but it is not something to which already there is an assigned value. We will have to assign a value, and that will be the sum of this series. In the ordinary theory of convergent series of real numbers, this expression will not be assigned any sum because it is a divergent series. We will see these things, or we probably already know about this thing. However, in the theory of summability of series, sometimes divergent series are also assigned some values. Okay, it's about assigning, so that's where the semantic comes. For now, however, there is no distinction between the one such expression and the value to which it corresponds. Okay, so that is the thing. In short, there is no distinction for us. That will be useful to us. Yeah, in the very next line, the author says that we need not bother about these distinctions. So what is he saying? However, we will not be very careful about this distinction, as it is purely linguistic. Yes. However, we will not be very careful about this distinction, as it is purely linguistic and it does not affect the mathematics, and thus and has no bearing on the mathematics. So for us, these two things are going to mean the same thing. The expressions, this series and 15, are the same number and thus mathematically interchangeable. Are the same number. And are thus mathematically interchangeable in the sense of the axiom of substitution. The axiom of substitution is something that you find in Appendix 7. So what the axiom of substitution says is roughly this. Say you have a set P of some objects of the same type. Okay, some objects are there, and you define a relation between any two objects of this set using some sort of definition, some rule by which some objects will be treated as equal in this set, although they may not be exactly the same thing, but they will be treated as equal. Now, that type of relation you already know. One such relation is an equivalence relation. But in order to turn an equivalence relation into a truly a sort of equality on this class of objects, we also need the axiom of substitution. To give you an idea of what this is all about, you think of the set of rational numbers. Okay. Now we know that in fact we have rigorously constructed the system of rational numbers from the integers. So we know that the rational numbers actually are like this. They look like this: a divided by b, where a and b are integers and b is of course non-zero. Now, when we constructed the system of rational numbers, recall that we started with this set actually. The Cartesian product of the integers with itself. On this set, we concentrated on those ordered pairs a comma b where b is non-zero. So in fact you can, instead of directly thinking of this as Q, you can think of this set as T. And on this set we then defined a sort of relation. What that relation tells us is that two such ordered pairs are related if and only if AD is equal to BC. We then proved that this relation is an equivalence relation, and the equivalence classes are actually the things that ultimately turned out to give us the system of rational numbers. So if you are thinking of these ordered pairs E comma F, say, where these are ordered pairs of integers where the second coordinates are all non-zero, then this relation defines an equivalence relation on this set. So according to this equivalence relation, the elements that are related will be treated as the same thing. That's how we have this norm, because 2 comma 4 is related to 1 comma 2, AD is equal to BC, 2 times 2 is equal to 4 times 1. So that is why these two corresponding rational numbers are treated as equal, and this equality is not literal equality. This equality is coming from this equivalence relation. But just equivalence relation, it is there, but there is something else also known as the axiom of substitution. What that says is that those elements in this class of objects T that are treated as equal will continue to behave in an equal manner no matter what function or what statement about them we bring in. For example, there is a function f defined on the objects of this class. You take the elements of this class as input, put that in the function will give you an output. What is the nature of the output? That does not matter. So say you have one x here, another x prime here, and they are treated as equal according to the equivalence relation that you have in this, on this class. So if you put x here in the function, you will get an output. If you put that x prime, you will get another output. These two outputs should be the same. Okay, that is the axiom of substitution. You should be able to substitute x prime in place of x and not affecting the result. Just like that, say p of x is a statement, a mathematical statement where you can put the x here. That statement depends on the elements of this class. You take one element, for that particular element this statement is either true or false. Now if it happens that this statement is true for this particular x, then for the equivalent x prime also this should be true. That is, these two statements should be logically equivalent. Either both of them are true or both of them are false. If you are able to substitute like this, I mean you don't have to think about what you are putting here in a statement or in a function. If you are putting something that is equivalent to something else that was already there, then there is no change in the truth or falsity of the statement or in the output of the function. That is the axiom of substitution. So that's what we are saying here, that they are mathematically equivalent, interchangeable in the sense of the axiom of substitution. In any function or any statement, whether you write this expression or you write 15, the result is not going to change. Okay, and the ultimate thing is that there is nothing to worry about. We will continue to treat them as equal as we have done all along. Even if, okay, there is something more in this statement, even if they are not, semantically interchangeable. Semantically interchangeable, we don't need to think about those things, okay? We can interchange them. That's just the thing. Then there is another remark. Note that the variable I, sometimes called the index of summation, is a bound variable. Sometimes also called a dummy variable. Bound because in a series expression, it's the values that it can take, I can take, have already been pre-assigned. I can take the values between the integers m and n, including the integers m and n. So it's called a bound variable, and that is also sometimes known as a dummy variable. Now the name you give to this variable, that does not matter. That's what this remark is about. The expression does not actually depend on any quantity named I. Yeah. The series expression does not actually depend on any quantity named I. That is, you can in fact use J also. In particular, one can replace the index of summation I with any other symbol and obtain the same sum. Yes. In particular, one can replace the index of summation I with any other symbol and obtain the same sum. Obtain the same sum. That is, if in place of I you decide to use j, then the sum that will be assigned to these two things will be the same. I think semantically they will be different. I don't have a clear idea of semantics and all those things, but mathematically they are of course the same thing. These are things we already know. Okay. Now next comes the basic properties of finite series in the form of a lemma. We can write like this. We list below some basic properties of summation. Okay, so the author is saying summation below, which just means what he tries to mean here is that basic properties of finite series. And the properties are things which we already know and we have used it many times already, these facts about finite sums. However, because we have rigorously defined in the definition, regardless of the fact that the definition has issues, we will rectify those issues, we will address them. But because there is a rigorous mathematical definition, so these properties will have to be proved. Irrespective of how natural they look. It has parts. Let m less than or equal to n, which is less than p, be integers. And let ai be a real number assigned to each integer I lying between m and p. Then we have this. Summation of ai as I varies from m to n plus summation of ai as I varies from n plus 1 to p is equal to the summation of ai as I varies from m to p. So it's just splitting this sum into 2. That's just it. B let m less than or equal to n be integers, comma k be another integer. K is any integer not related to m or n, and let ai I think I could use some ink first. ai be a real number assigned to each integer lying between m and n. Then we have our series is equal to, we can change these numbers, and we can also change this what we write in place of I without altering the sum of the series. J is varying from m plus k to n plus k. C. The starting is almost always the same. Let m less than or equal to n be integers, and this time we have two sequences of real numbers, and let ai comma bi be real numbers assigned to each integer lying between m and n. Then we have it's this one. AI plus BI this is equal to summation AI plus summation BI. Then D let n less than or equal to n be integers, AI be a real number, assigned to each integer lying between m and n, and let C be another real number. Then we have summation CAI is equal to C times summation AI. Two more parts are there. Part E is called triangle inequality for finite series. It has a name, and the name says it all. And let AI be assigned to each integer I lying between 1 and n. Then we have the absolute value of the series. Oh, sorry. See, that's what happens when we become accustomed with infinite series. The tendency is to write infinity, because mostly we are working with infinite series. and then there is one more, which is comparison test for finite series. These names may seem like somewhat useless, given that we already know about these things a lot. I mean, at least we know that these things are true, and the names seem somewhat strange, but the names have been given here in order to show that similar things are also there in the theory of infinite series, and the same type of name help us remember that both the things are true. So you can in fact see in this name comparison test for finite series. Actually, when we have an infinite series, there comes the question of its convergence or non-convergence, divergence. So there is a test for seeing whether a given series is convergent. So one such test is a comparison test. Here, however, for finite series, there in fact is no issue of convergence. We will see these things when the time comes. So just like that infinite series version, here we have this. Let this be integers ai, bi, p real numbers assigned to each integer I lying between m and n, such that there is a condition ai is less than or equal to bi for each I in that range. Then we have the corresponding series also behaving in that way. They also follow a similar inequality. And these things have to be proved, and the proof is left to us. It is in fact the first exercise. So we will do it then when we start solving the exercises. So let's now finish with one remark. In the future, we may omit some parentheses in series expansions. series expression, sorry, in these expressions. For instance, we may write simply as this. Without using those round brackets. This is a reasonably safe simplification of notation, and it's safe from being misinterpreted. The only misinterpretation that possibly can be there because the alternative interpretation that this expression actually means this. This is meaningless, this does not make sense. That is because here the index of summation is there in this series, whereas at the same time it is outside. So when I varies between m and n, this I changes, however this does not change due to the fact that it is outside. So that is meaningless. The index I in bi is meaningless outside of the summation. Since I is only a dummy variable, so you can apply the axiom of substitution here. In place of I, you can write j. However, if you do that here, then everything will change. That is the thing, is that when there is an index of summation already in a summation, and this is something else actually, then do not use I there. Okay, that will create extreme confusion and everything will go down. So let's just end the video here. In the next video we will see how this infinite series can be used to define the sum of the elements of a finite set, which are of course numbers, and how such a sum is well defined. And then we will see similar properties that we have seen today in this lemma about finite series. Similar properties are true for finite sums also. And coming Tuesday we have number theory. Already we have done it once, so graph theory. So I am just ending things here itself. If you want to say something about these things or about anything else related to mathematics, you can write in the comment section below, or you can mail me at my usual address, which will be there in the description. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.